Okay, so now we'll see some parametric interval Markov chains. So up to now you've seen material about parametric time automata. You've seen that we need maybe sometimes some parametric probabilities in order to capture imprecisions, robustness, and dimensioning issues. So we'll introduce in that sequence, we'll introduce parametric interval Markov chains and their properties. So first of all, what is a Markov chain? A Markov chain is something like this example, where you have states and probabilities to go from one state to another one. So for example here, to go from state 0 to state 1, you have a probability 0.7, 70% to go from 0 to 1, and 30% to go from 0 to 2, here 30%. So that is basically what is behind a Markov chain. Now, these can be specified in a more larger scheme with interval Markov chains. So you can see interval Markov chains as larger specifications, and instead of having single probabilities like here, you have an interval of probabilities. So in an interval Markov chain, you would say that the probability of going from one state to another is some probability within an interval. So here from 0 to 1, it's a probability between 0 and 1, and from 0 to 2, it's also a probability between 0 and 1. So in this case, well, you don't know the actual value, but you know it's bounded in some interval. From 0 to 1, it's not very interesting because it's all possibilities of probabilities. But for example, if you want to go from state 1 to state 3, you can see that here you have a probability that is between 0.3 and 0.5. So any probability between these two numbers can be taken. And actually you can see that if you have these two examples, the first one is a Markov chain that implements the specification, the interval Markov chain. Indeed, if you look at the values on the arcs, here you have 0.5, here you have 0.5, which is in the interval 0, 3, 0, 5, and so on. You can notice that between 2 and 4, so here, you have an interval that is bounded by, where the lower bound is 0 and the upper bound is 0.5. So you can choose to say, well, I have a probability 0 to go from 2 to 4, which is the case in this implementation, right? So disabling the 4, and thus you don't have anything going from 4 to 3 as in the other, in the specification. Okay. So we say that an interval Markov chain is consistent if it admits at least one implementation. And the consistency property is the most important properties we'll have here. So we'll look at it in detail in the following. If we want to extend this, because we don't know the actual bounds, we can use parameters. And that is the case here in parametric interval Markov chains, or PIMCs for short. You can notice that here we have some parameters, Q and P, and these parameters are either the lower bound or the upper bound of the interval. They also can appear at several places, so you can see you have Q here, but also you have Q here. So it would say, well, this same probability is used as a lower bound for the first interval here and an upper bound for the second interval here. and it can occur at different places. Okay, so if you evaluate these parameters with some actual value, then you will get an interval Markov chain, because you have given values, so it's simple. Okay, so the property we'll be interested in these models is consistency. So let's look at consistency for interval Markov chains first. We say that a state S of an interval Markov chain is zero consistent, so that will be the basic property. If there exists a distribution, probability distribution over the successors of the state S, that matches the intervals. So there exist values that match the intervals, and everything is going fine locally. But then we want to know the repercussions of choices in intervals on other states or of the model. So we'll say that a state S in an IMC is n consistent for other values of n other than 0 if there exists a probability distribution over the successors that matches the intervals, and if the successors S prime of S are such that if their probability, the probability to reach them is positive, then they are n minus 1 consistent. So you can either choose to disable something, saying, well, I choose a distribution that goes from one state S to a state S prime that is 0, and then I choose to disable this transition because I'll have a probability 0, or I choose to keep it, and so I don't choose the probability 0, but then I must ensure that the state I reach is n minus 1 consistent. And there's a theorem saying that an IMC with n states is consistent if and only if its initial state is n consistent. So there is an implementation and so on. So let's take a first example. Here we have the same example as we had at the beginning. And in this example we can check the zero consistency of all states. So let us look at state 4. State 4 has outgoing probabilities of 0.6 n, so it's the interval 0.6, 0.6, you don't have the choice, same lower bound and upper bound. And another transitions exiting the state 4, that is an interval 0.51. So if you want to look at the possible probabilities, the possible distributions outgoing state 4, you'll see that the lower bound is 0.6 plus 0.5, and it is 1.1. Oh. So it's bigger than 1, and it's not possible. So in fact, this state 4 is not zero consistent. So we have denoted it here with button. Okay, so it's not zero consistent. Now let's take another node, let's say state 1. So state 1 is an outgoing probability between 0.5 and 1, and another one here between 0.3 and 0.5. So the minimum of the lower bound will be 0.5 plus 0.3. So 0.8, it's smaller than 1, so we can have something smaller than 1. And the upper bound is 1 plus 0.5, so something bigger than 1. So we can find values in these two intervals so that the sum of them is 1. And therefore, state 1 is zero consistent. Okay. And we can check the same for all states. Now, if we want to check one consistency, here we know that 4 was not zero consistent, so we'll try to avoid getting to 4. And this is possible because here we have 0 in the interval. So we can choose having the probability 0 from node 2, state 2 to state 4. If we choose 0, let's look at what is remaining. So we have an interval 0, 0.5, and another interval 0, 0.5. So if we sum that, we'll have 0 as the sum of lower bounds and 1 as the sum of upper bounds. So it works. We can choose values so that the total is 1. Okay. So 2 is one consistent. And you can repeat the same procedure for all nodes, and you'll see they are all one consistent. And in fact, they are all n consistent for n bigger than 1. Well, except state 4, that is not. Okay, let's take a second example. In this second example, you can see that node 2 is not 0 consistent. And why is it the case? It's because we have this interval 0.3, 0.4, and the other outgoing interval 0, 0.5. So if I do the lower bound, I will have 0.3, and the upper bound 0.9. So I can't get a distribution that adds up to 1. So state 2 is not 0 consistent. Concerning the other states, we can see that they are both 0 consistent. The lower bounds are smaller than 1, and the upper bounds are, well, the sum of upper bounds is bigger than 1. So let's look at one consistency. So state 2 is not 0 consistent, so I would try to avoid state 2. But you can notice that here, I cannot choose 0. So I cannot choose to avoid state 2. Therefore, the condition saying that the successors that I keep, which have a probability to be reached that is not null, are n-1 consistent, so in this case 0 consistent, and therefore state 1 is not 1 consistent. As concerns state 0 can reach state 1, and it can loop on itself, and it is 1 consistent because the sums add to something lower than 1 for the lower bound and bigger than 1 for the upper bound. Now if I want to check 2 consistency of state 0, you can see that state 1 being 0 consistent but not 1 consistent, I have to avoid it, and I can pick 0 in this interval. What remains is only the loop here, and this loop is as an interval 0.5, 1, so I can pick 1 as a probability, and I'm happy with state 0. Okay, so at this stage you've seen a parametric interval Markov chain, the model, and you know how to check consistency for interval Markov chains. So what we'll do is in the next sequence to check consistency for parametric interval Markov chains.